right, we'll go ahead and get started. So welcome back to part 2 of how to build a cloud data platform. A few housekeeping items before we begin. So the best way to ask questions throughout, Doug will be answering questions throughout the presentation, is through the Q&A box, which is at the bottom of your screen in the control panel. So please feel free to submit questions there. Again, if we don't get through all of your questions, we will make sure to follow up with you as soon as possible. You should have received a recap email yesterday afternoon/evening, depending on where you are, which had the on-demand link to the session yesterday, as well as the coupon code for free training, or the link, should I say. As a reminder, this is the same Zoom link for the sessions for tomorrow and Friday. So please use the same Zoom link. And finally, we will have a survey next week, which will ask you about your experience. So please participate in the survey so we can continue to deliver high quality training and programs for all of you folks. With that, we will turn it over to Doug, our lead instructor at Databricks, who will take you through today's session. Doug, take it away.
All right, thanks, Kayla. I'm going to go ahead and share my screen. Take me just one moment. There we go. All right, so welcome back. This is part 2 of our 4-part series, how to build a cloud data platform for BI and ML. I'm your instructor, Doug Bateman. Now, just a little bit about me in case you didn't attend the first session. I'm a principal instructor here at Databricks. I joined Databricks 4 years ago, and in Databricks time, that is an eternity. Back then, we were roughly 50 people, and now we are significantly larger than that, in the several thousand. We are growing very, very quickly and really taking the internet by storm. With that said, I have roughly 20 plus years experience architecting and delivering large systems, as well as training and consulting. And I always like to introduce myself as a human being as well. So I have 2 children, 1 and 4. They're downstairs playing. Hopefully we won't hear them. And if they come, they'll say hi with the working from home. And for fun, I enjoy sailing and rock climbing. And occasionally we get out to Tahoe to go snowboarding, although I won't claim to be a terribly amazing snowboarder. I do enjoy it. And in my spare time, I enjoy playing chess. I'm actually a volunteer administrator at the Internet Chess Club. But I certainly wouldn't claim to be terribly good at chess, but it's still a fun hobby of mine. So that just introduces me as a person, as well as an instructor here at Databricks. And what I'd like to do now is to introduce the series. This is part 2 of our 4-part series on how to build a cloud data platform. Yesterday, for part 1, we talked about the architecture. Really, what does a cloud data platform look like? What are all the tools involved? What does the processing pipeline look like? And we set up the big picture so that today we can dive in at a coding level and actually start constructing such a pipeline. And the construction of our pipeline will take up parts 2 and 3 of this series. So we're going to get as far as we can today, and then we'll continue with it in part 3. So today we're really targeting doing ETL processing and loading the data into our pipeline. So we'll read some JSON files, we'll upload them to Databricks, read some JSON files, write them out first as Parquet, and then we'll actually convert our Parquet files into Delta tables instead for higher performance. And then we'll start dealing with other challenges that come with ETL. For example, dealing with late arriving data or repairing corrupted data, which are standard challenges that people deal with when they're building their data warehouse and doing ETL. And then part 3, we'll continue with that, and we'll introduce the structured streaming component. And structured streaming is incredibly powerful because it allows us to work on deltas, what's changed in each table. So rather than having to read the entire table, I can say, read what's changed since last time I ran this job and process that. And so we treat this as a constantly changing streaming source, reading each table and writing to the next table downstream. And then we'll also work with some of the capabilities of Delta when it comes to accessing past versions of the data and how would you scrub past versions of the data for GDPR compliance. GDPR being the European regulations for privacy. And then part 4 is where we're going to look at downstream consumers of our Delta Lake. So these people will be doing, for example, machine learning. So I want to consume the data lake that I've spent all this time doing ETL into, and now I want to build machine learning models and track my experiments using MLflow. Or maybe I want to use a business intelligence tool to run SQL queries against my data lake. And so that will be part 4 of this 4-part series on Friday. Now, a number of people have asked, where can we go to get access to the materials that we are using for this course? And the answer is we are uploading them to this website here, tinyurl.com/cloud-data-platform. And if people ask in chat, that's the link that we're going to send you to as well. In fact, well, I can't copy easily. But tinyurl.com/cloud-data-platform. Let me go ahead and type that into the chat area. That is if I can successfully get access to the chat area. Here we go, I found out where it's hiding. And you can go here to access the data at any time. And we will be, if I create notebooks and things of that nature, we will upload those there as well. So what does that look like exactly? And the answer is, if you go to that URL, you're going to come here to academy.databricks.com/pathway/how-to-build-a-cloud data platform. And we are making it available to people who attend the webinar. So this link is just for people who attend the webinar. That's you. Or if you're watching this recording live or recording afterwards, then you come here and you can get access to what we would normally charge people for, but you get it free because you're here part of the webinar, and you can actually sign up and enroll. So you would click start and you'll be able to enroll in the course. And at that point, you'll be taken to a page where you have access to both the materials that we used yesterday, which was fundamentals of the Delta Lake, as well as the materials that I'll be using for the next 2 days here, which is the Delta Lake Rapid Start. And as we create additional materials, such as the demo notebook that we did yesterday, those will be uploaded to this page as well. So that demo notebook from yesterday, we're working to get uploaded to this website right now. So this gives you kind of an idea as to what's available. And yesterday, as you recall, we had worked with the fundamentals of Delta Lake, and that's what you'll be able to get access to by going to this page. And similarly, today, we're going to be working on the Delta Lake Rapid Start with Spark SQL. So this is where we're going to be using Spark SQL to construct our Delta Lake. So we're going to be building our cloud data platform. And you're welcome to follow along or simply enjoy the show today while I'm doing the webinar, and then come to this webpage afterwards to try to do this yourself, which is what I would recommend because it makes it a little bit easier to pay attention and follow along. So with that in mind, let's do a short recap of yesterday. So yesterday we introduced who is Databricks. So Databricks, we are really a big data company. We're the original creators of Apache Spark, as well as the Delta Lake file format and MLflow. And these are open source projects that are now available to anyone on the internet with contributors all around the globe. So we don't like to say we're the creators because all of the people in the world who have contributed any line of code to one of these projects is a creator, but we were the original creators who put it out there and available and online. As we like to say, Spark, I am your father. Okay, that was my attempted humor for our morning webinar here. Now, of course, some of you guys are going to be in Europe, so it may not be morning where you are, but it's morning here in California. And we have thousands of global companies using our platform across big data and machine learning, and it is scaling and growing, which is just really amazing. And our goal is to accelerate innovation by unifying data science, engineering, and business using what we call a unified analytics platform. So what is a unified analytics platform? Well, we're going to be seeing it today, But it's this idea that you've got one platform that's able to do a variety of different workloads throughout the data analytics lifecycle. So that means ETLing the data into a data lake or our cloud data platform, which is what we were looking at yesterday on our presentation, the architecture for that, and we'll be doing today. So we construct our data lake that we can then query after we do ETL workloads. And then once we've built that data lake, we want to be able to do exploratory data analytics. So you saw that we were able to use notebooks and make plots yesterday in our previous webinar in part 1. And as well, you're able to do machine learning activities. This is what will be a focus of the 4th part of our series, doing machine learning. And there are other types of workloads that we can do. For example, updating the data on a continuous basis using live streaming, which is really, really cool. And then graph processing, that's where you have nodes and edges like flights and airports, and you're doing some type of analytics that goes with that. So Apache Spark, again, was that unified analytics engine for big data processing with built-in modules for streaming, SQL, machine learning, and graph processing. And it started out in 2009, and now it has really become a de facto technology for building our data lakes. We also reviewed just briefly yesterday the way in which Spark breaks up the data. So Spark works by your code, your application is running in the driver, and the driver then takes the queries that you write and comes up with an execution plan that in turn is divvied up amongst various cluster machines called executors. So a cluster consists of a driver and one or more executors that is then used to run our workloads. So one driver and many executors. And the executors in turn each run on a piece of the data. So they'll read in some of the data from outside. They'll read in data, process it, and write it back out to disk so that no one machine has to deal with all of the data. And this gives us scalability where we can scale out when our data is too big to fit in a single machine. And then yesterday we talked about where this really fits into the world. And so back in the 1980s, people were using software systems, and the field of data warehousing really became popular. Bill Inman had written whole books on the idea of data warehousing. And this is the idea that I've got all sorts of different data stores that contain my operational data, and I may be pulling from other systems as well. So I may be doing snapshots of the operational data in my operational data store. But at some point, I want to ETL that data into my data warehouse. And so our data warehouse is pulling data from all across the enterprise with these ETL type workloads. And there's this entire process where you bring the data, you load the data in, then you do some data cleansing, and eventually you end up with these data marts that are used by departments to be able to do their business intelligence and reporting. And the field of data warehousing is incredibly popular when it comes to analytics, but there's challenges that we need to address, such as scaling up these software systems, as well as the diversity of file formats that we have to deal with. So a traditional data warehouse required that we set up our enterprise schema. It's highly structured. And as a result, there's a lot of work that was required to do the ETL up front before we could start getting any types of insights. And so with the advent of Hadoop, the data lake had become a really popular platform. And the idea of the data lake is that we simply store this data initially as it's being exported into a really large storage bin. So we could be using cloud storage systems such as Amazon S3 or Azure Blob Store or Azure Data Lake Store. But what we're really doing is dumping this data out there so that it could be used and available for people, and we don't worry about cleaning it up front. We're simply capturing it. We're getting it out of these systems and we're capturing it, but we delay the cleansing. And the reason we delay the cleansing is that if we tried to do all the cleansing up front, we would spend all of our time doing cleansing, and people would decide that it was just too hard to use our data warehouse because we spend so much time doing data cleansing, and therefore we're just not going to bring in the data in the first place. So the idea is, no, let's just capture the data as it is and then start doing ETL workloads on that data later when we're actually interested in it. So you clean the parts of the data that you actually are interested in, and you bring it into these data marts, which can be a data warehouse, or it could simply be tables that are part of our cloud data platform. And then you do your reporting and analytics on that. Now, the cloud data platform takes this data lake paradigm from Hadoop and goes even further and says, let's use Apache Spark, and let's actually have our cloud data platform store all of the data. So, and let's actually store it in the cloud where we've got this elastic compute and elastic storage. So we're going to have the cloud data platform keep everything. And in fact, when it comes time to do things like data marts, we'd really like to see if we can use Spark to be the data mart. That is the consumer part of the data warehouse. But if I need faster responsive queries, I might still end up having a data warehouse in here as well, in terms of just reducing the response time for interactive queries, because there is a little bit of a latency when you're working with something like Spark and our cloud data platform. But for the bulk of the ETL, we really want to use the cloud to do this and host this using Apache Spark. And so what does that look like exactly? So, oops, there we go. So what this looks like is that we're using Apache Spark to do ETL workloads from all of our various sources of data. This could be our operational data store where we've got snapshots from various systems, or this could be pulling from the actual systems themselves. And as we pull data from the various systems, either by streaming or by reading from databases or just file formats that have been dumped into a directory, we're going to ETL that, and we're going to talk about the layers again in just a moment, but we're going to ETL that into our data lake using a really powerful query engine like Apache Spark. And then we're going to use an interactive notebook environment like a Databricks workspace to be able to query that data and extract insights. So our end users can log into the workspace, begin doing those types of queries. Additionally, an end user might prefer to instead use a tool like Tableau, and Tableau in that case would just be sending JDBC queries to Databricks, which in turn would be servicing those queries from the actual data lake. And the beauty is that we have really cheap storage for all of this data, and we're only paying for the CPU cycles that are needed to run our workload for today. And then we shut down our clusters. And we had talked a little bit about this pipeline, the idea that when we do the ETL, the first goal is just to capture the data as it's coming in, not do any cleansing. Some people call these their loading tables. At Databricks, we like to think of it as kind of levels of data quality. So we tend to think of it as our bronze layer. It's the data in its raw, ugly format. It's everything. It's a lot of it. And the idea is just capture it. Don't worry about cleaning it yet. Just make sure you don't lose it. Store it in this cheap data storage. We'll come back and grab it later when we're interested in it. And then as you start getting interested in the data, you're going to find that you need to do data cleansing. And that's where the silver tables come in. It says, what I'd really like to do is clean up this data, deal with late arriving records, corrupted records, put things into a flatter directory structure because it may have come in JSON and it's a little bit tedious sometimes to query JSON as opposed to flat tabular structures. So I might move this into tables that are flatter. I might move this into something that's closer to a third normal form, although it doesn't have to be. And these are my query tables, basically my functional enterprise data warehouse. And my data is here, and people can go and query that data directly. But there's still a lot of data, and we may want to do some types of aggregate rollups. So we may want to produce a star schema, for example, that really takes that data and does aggregations. And so we might have a nightly job that reads those silver tables, does various types of reporting on it, and generates easier tables that are either featureized for machine learning or aggregated for reporting purposes and business intelligence. And we'll create an even higher, what we would call a data mart in data warehousing lingo, or it could be featureized for machine learning, but our more refined data in terms of data quality. These are our gold tables and ones that we would really like our end users to be accessing. So most of the time, our end users who are doing reporting would like to be reading these really polished gold tables. On occasion, they may say, oh, I've got a query that's not available in those gold tables because I'm trying to drill down and get more insights. And they might access these clean data. And then on rare occasion, they may say, there was data that nobody thought we would be interested in, but boy, I'm glad I saved all that raw data because I really am interested in this extra data point. Let me bring it into my system. And you can, in fact, go and query the bronze tables, although what you typically would do would just be to bring that extra data when you're interested in it into your silver tables. So you're constantly improving your data pipeline. You've captured everything, and now you're loading the parts that you're interested in. And this is what allows us to capture everything, which is the benefit of the data lake, while still getting data cleanliness, which was the benefit of a manicured data warehouse. But to do this, there are challenges that we need to overcome. And some of those challenges have to deal with managing this ETL pipeline, dealing with late arriving data, making sure that when I do one of these workloads where I'm reading data from bronze to silver, that the job is reliable. So if it fails halfway through, I don't want half-written data to my silver tables. I need an all or nothing. I want to be able to enforce data cleanliness constraints. I want to be able to also work with, tell me what's new in my bronze data store, and ETL just the new stuff. So is there an easy way where I could track the changes, the delta of what was in that table before, and only work on what's new? And that's where streaming is going to come into the picture. So this is what we talked about in terms of the architecture in the previous webinar. So today our goal is going to be to construct this type of data lake experience in our cloud data platform using Databricks. So we're going to drop down now and it'll go into the coding layer. Let's see here. Before we do, I'm just going to take one question and answer it. Somebody had asked, because we did a lot of our examples using Spark SQL, and somebody asked, what's the difference between PySpark and Spark SQL? And I do actually have a slide on this. It was one that I wasn't going to cover, but I'm going to go ahead and bring it up now because it will help address that question a little bit. So first of all, let me just show what PySpark looks like as opposed to Spark SQL. So in PySpark, notice I'm using Python as opposed to SQL to describe my queries. But at the end of the day, I'm simply describing my query. Whether I choose to use SQL to describe my query or I use Python to describe my query, at the end of the day, I'm just describing a query. So in this case, my query is I want to group this data up here by name, and then I want to get the average age. But I'm just describing a query. Now, this particular slide was really designed to be contrasting this data frames approach where you're describing your query to an older Spark approach called RDDs. RDDs are the underlying, almost like assembly layer. It's the low level in Spark that we don't often work at. And the reason we don't work at the RDD layer is because it's not very readable. So if you look at this code, if I was trying to do this using functional programming, I'd be passing in a function here saying, grab that data, run this function, run this function, and run this function. And it's really hard to know what that code is doing compared to this code down here in PySpark, where it's really clear I'm grouping the data by name and averaging the age. So it's a declarative query as opposed to a functional-oriented programming paradigm. So we really like working with data frames in PySpark as opposed to the RDD level. In fact, we're not even going to talk about RDDs as part of this webinar series. But the reason I'm talking about this is I wanted to show PySpark because I wanted to show how PySpark fits into this picture here to answer that question that came up. Whether I'm using PySpark and the data frames API, or I'm using SQL, at the end of the day, I'm just expressing a query operation or a data operation. So I'm either doing data manipulation or data query, but I'm expressing in a declarative way what I want to do with this data. And then the driver takes all of this stuff and goes through a whole planning process where it generates code. So it's going to look at your query, whether you describe your query in SQL or in Python, it gets fed into the same process here. So there's really no difference as to whether I'm using SQL or Python. It's getting fed into the same query planning process where it goes through a rule-based query optimizer, and eventually a physical plan pops out on the other side that Spark turns into an RDD and runs. But this RDD that Spark generates is way more efficient than any RDD you could have written yourself, because it generates code. It's actually generating code on the fly that works on native byte arrays. And you could just not, it would be incredibly difficult for you to write an RDD that would be as efficient as the stuff that Spark generates for you. Just how much more efficient? Take a look at this slide here. So if I was doing RDD programming, look how long it takes to run a job. And if I was doing RDD programming, Python would have been slower than Scala. But when I go to using data frames, Spark is generating code, and it's generating code that's much more efficient. So it doesn't matter whether I use SQL or Python, I'm going to get all of the benefits of that query optimization process. So the short answer is choose SQL if SQL is comfortable to you. Choose Python if Python and PySpark are comfortable to you. In this series, I'm going to choose SQL because it appeals to the broadest part of the audience. But when we get to streaming and to machine learning, we will drop to Python at that point because those APIs aren't available in SQL. The machine learning and the streaming APIs will require some Python. But for the rest of this, I'm going to use SQL because it's just accessible and it's there and it's easy for people to work with. But notice that the performance is the same. And for those that are really advanced, I'll make a footnote. If you define a user-defined function, user-defined functions are the one place where there's now a cost associated with using Python because that user-defined function is written in Python. Now, if you write your user-defined function in Scala, it will be faster than if you wrote it in Python. We're not even going to be looking at user-defined functions, but I wanted to make that footnote. And if you wanted to learn more about user-defined functions, I would encourage you to go to academy.databricks.com and take some of our SQL courses where we really go deeper, especially our ETL series of courses in the academy.databricks.com, and you'll learn more about user-defined functions. All right, so with that in mind, let's go ahead and start building our data lake here. I'm gonna leave this slide up for a little bit later. All right, so remember I told you you could go to that link, that tiny URL that we put up earlier. It's tinyurl.com/cloud-data-platform, and it's going to take you and make available to you access to the online course. And at that point, you'll see the fundamentals of Delta Lake, which is what we covered yesterday. And for the next 2 days, we're going to be working from Delta Lake Rapid Start with Spark SQL. So in the Delta Lake Rapid Start with Spark SQL, this is where we're going to be working today. We're going to actually be building our data pipeline. So again, remember this picture that we had from yesterday, where we might have, in this case, we've got a scenario where we're going to be working in the Internet of Things. So our data set is going to be health tracker data. So we're talking little, fitness watches that you might wear on your wrist. We've got health tracker data that's coming in from our Internet of Things. So we've got JSON files being collected from a whole variety of different systems. And our data is going to start out coming in as JSON files. And this would be really what we would consider our operational data. So in this case, the health tracker data has been streaming in. Somebody dumped it into our operational data store. This is using a traditional database, or what we call online transaction processing. Online transaction processing is where you are editing and modifying individual rows of a database. And we don't use Spark for that type of workload. We use a regular database. When you're doing any type of workload where you're just updating 1 or 2 rows, 1 or 2 records, we would use a traditional database. Where we're going to use Spark is when we're doing the analysis, the online analytical processing from our data warehouse, where we're running huge big data queries. So what we're going to want to do is ETL the data from that operational data store into our data warehouse so that we could do this type of analytical query, as opposed to the individual row updates that are needed when I'm writing data to that operational data store. So this is the idea of ETL, and we're going to be using Apache Spark to do this ETL, and then we're going to go and build that single source of truth, and eventually we're going to build out those data marts as gold tables for analytics purposes. So we'll have our silver tables and our enterprise data warehouse, and eventually our gold tables doing analytics. And again, Delta Lake and Spark are not used for a transactional database. You're going to use MySQL or some other database for that type of work. We are going to use Spark to build the data warehouse, or our data lake in this case, our cloud data platform. So we're going to use Spark to do ETL, building out that single source of truth and maintaining it, keeping it up to date, and building out those data marks. So in this particular example, the first thing that we need to do is to create a database in our system. So I'm going to come over here and I'm going to say create. First of all, I'm going to remake this notebook. I had made this notebook in Python, and that was a mistake because I'm going to use SQL as my primary language. So when I log into Databricks, whenever you first create your account, you're going to get a workspace a bit like this. In fact, if you wanted to have your own workspace, if you go to databricks.com and you click on the Try Databricks button, you're able to sign up for Databricks Community Edition. And at that point, you would log into community.cloud.databricks.com and you'd have a workspace that looks a little bit like mine. Today, I'm going to use not just the Community Edition of Databricks, but the full version of Databricks because it's got additional features and allows me to launch larger clusters that'll reduce the latency of some of the jobs that we're about to run. And you'd launch a cluster by clicking on the Clusters tab. And in this case, here's Doug's cluster. And I'm running Databricks version 6.5 machine learning runtime. That means it comes bundled with a bunch of machine learning libraries. And that's running Apache Spark 2.4.5 on Scala version 2.11. So even though I might be using Python, underneath it gets compiled into Java and Scala code. And I set my cluster to have 2 executors. Each of these are going to be quite large in this case, a 64-core executor. And then I click on Home, and I'm going to say I want to create a new notebook. I'll create a new notebook, and I get to pick the programming language. And in this case, the programming language that I'm going to be doing is SQL, and this will be my Internet of Things project. Choose SQL for my default programming language, and I choose my cluster. And Databricks has been doing a lot of contributions trying to help do analysis of COVID-19. So you'll see that some other people at Databricks are running a cluster that's doing that type of analysis. But for now, I'm going to just be creating my own cluster that I'm not shared with anybody else and connecting to that. And now I want to start ETLing in my data. So the first thing I need to do is to create a schema where I can start uploading my tables. So I'm going to say create database, if not exists, DB Academy. And use DB Academy for my tables. Let's see, create database if not exists. There we go. And now I could look to see what tables I have in here. So show tables DB Academy. Or just show tables in this case. And currently I don't have any tables in the DB Academy schema. So we need to upload our tables. So I'll click over here on data and I'm going to click add data. And I'm able to upload a file. So I'll click browse. And here's my health tracker data. So I'll upload my health tracker data 2020-01.json. And where do I get that data from? You may be wondering. So if you're actually taking the course, so if you've got that course open, it's going to show you a place that you can actually download these JSON files that I'm using. So if you're doing this after the training, you're welcome to download those files. So I'm just going to upload them to Databricks. And then I say create table with the UI. I choose my cluster, Doug's cluster, preview table. And here's the file that I uploaded. It's put JSON because it's a JSON table. I'm going to strip off the name JSON just so that I can match the course. And I say create in database. And where is DB Academy? DB Academy. There we go. And then I check infer schema. So it's going to look at the JSON file and it figured out which columns are integers, which columns are doubles, which columns are strings, and so forth. You'll notice the time it's decided to infer as a double. And I click Create Table. All right, so now we've uploaded our first file. Let's upload the other two as well, just so that we're ready to go. So I click Add Data, Browse. We'll grab the second month's worth of data, create, choose my cluster, preview. Database is DB Academy, infer schema, and I say Create Table. And then last but not least, create the last table. All right, so I've uploaded these tables. Now it's possible that these tables were so big that I wouldn't want to upload them from my local machine. Maybe they're already out on the cloud. Well, in that case, instead of uploading a file, I could have pointed it to a file that's already out there on Amazon S3 or in the Databricks file system. So I can mount S3 buckets to the Databricks file system. And I could have loaded the data that way as well, which is really, really nice. But now I've got my tables. Let's go back to my notebook at this point. So we're going to find our Internet of Things and do Show Tables. And here are my three tables. Health tracker data 001, 002, 0, and then 02 underscore 01. And I could do describe extended, and the name of my table. And notice that it tells me this table is JSON, and it is located here in DBFS, the Databricks file system. And this Databricks file system is just a thin layer on top of my blob store, whether it's on Amazon S3 or Azure Data Lake Store. But here's my file, here's a path to the file. So if I actually wanted to, now that the file is actually in the Databricks file system, I could also have dropped the table. I could say drop table, health tracker data 2020-01. And then I could say create table if not exists, using JSON, location, and options, infer schema is true. And I could be creating the table using SQL instead. Drip table if exists. There we go. And I've created the table using SQL as opposed to using the UI. So I wanted to be able to show you both approaches to doing it. So I've got my tables. In fact, I will create the table a second time just for demo purposes. I'll put a B at the end so that you can see that it's there. I'll do show tables, and there's the table that I just created. It's just a duplicate. And then if I no longer want it, I could drop table health tracker 001B. And now if I do my show tables, it's no longer there. So this is how I get my data available to me as a table. Now keep in mind that this table is really backed by that JSON file. So if the JSON file changes, my table has changed. And every time I read this table, I'm really querying the JSON file. So let's do select star from health tracker 001. And there it is. This is my data. I've got, the device I'm looking at, its heart rate, who owned it, when did I capture this heart rate, etc. So this is my Internet of Things data for a health tracker. And I've brought it into my Delta Lake. And now somebody asked me a question: does everybody have access to this Delta Lake or Delta Layer? So this is Rahini's question. Rahini, the answer there is that the Delta Lake is the implementing technology for a data lake. So a data lake may include Delta files. It may also include JSON files. So in this case, my data lake is got JSON files in it currently. This SQL table is not currently a Delta table. So that answers Shlomit's question. This is not currently a Delta table. It is in my data lake, but it's backed by JSON at the moment. But notice that because it's registered as a table, people have access to it. Now, if you have the enterprise security package at Databricks, you can even attach ACLs, access control lists, to individual tables in Databricks, which is really nice. Other people are asking, how do you refresh these tables on a schedule? We will actually dig into how do we go about refreshing tables on a schedule, because we're going to be doing various jobs to refresh them. But this is where the jobs tab in Databricks comes in, because you can set a schedule to run code that's going to be refreshing the tables. But keep in mind, right now, this table is in fact a JSON file. So Databricks is not and Spark is not a database. It's a query engine that's working on top of these underlying files in our data lake. That's a really important distinction. All right, so let's keep going at this point. We've uploaded our files, we've made this data available, and we would like to just take a quick peek at it. So let's do a plot, select star from health tracker data, and let's make a plot out of it. So I've already done the select star, but I could come in here and do a bar chart. And right now, the bar chart, it just kind of picked which columns to use. So we could see how much data I have for people. And in this case, it summed up the time column. Well, that's not at all the plot I want. So I come here to plot options. And what I really want to do is look at, let's see here. Let's look at the chart we're aiming to get. I want time along this axis and heart rate along this axis. And I want to split it up by device ID. All right, so I'm going to make the keys be time. I'm going to make the heart rate be the value. And I'm going to split this up by device ID. And now I click, and I want to look at the number of data points that I have. So I'll go to count as opposed to summing up your heart rate. I want to look at how many heart rate measures I have. And now I click apply. Let me just compare that here to the course. So the course looks like it was actually looking at the average heart rate. No, it aggregated by sum in the course. So maybe instead of doing a count, I'm going to do average. And now I can look at people's average heart rates. There we go. And this is a little disturbing. I've got some data points in here where I have a negative heart rate. I guess that means your heart is beating backwards. Well, clearly this is bad data that we're going to have to clean up as part of our data cleansing process. So let's continue on here. I'll click continue. So the first thing we want to do is keep in mind, JSON is fine for our ingest process, but it's a very slow file format to read, because every single time I run this query, I've got to parse the JSON file. Just to illustrate this, let me expand the Spark job. And let's come here to the second Spark job and take a look at what this looks like. Actually, I'm going to come to the SQL tab, and I'll look at this query that we just ran. And notice that here, it's scanning the JSON file. So it's reading a JSON file every time I run a query. So it's got to parse that file every time I run a query, which is not very fast at all. But then you could see I'm filtering out data. I'm selecting only the device ID, the heart rate, and the time. I'm then doing a group by operation so that I could do the average heart rate. And eventually I get my final result that I'm displaying in this plot. So you can actually view the physical query plan. You could also view that query plan as text down here. And that's all available inside of the SQL tab when I view the job details. And somebody who wants to learn how to do performance optimization will need to learn how to read these query plans to figure out what is taking so long in your query. And you could do performance optimization using that part of the UI. That's beyond the scope of what we're talking about today. All right, but this is my query, and you could see that I was able to successfully run it. But the first thing I'd like to do would be to get it into a faster file format. Now, just for the benefit of making a narrative, we'd like to first turn this into a Parquet file. Now, in truth, I would rather use a Delta file format. But a lot of people already have their data out there in Parquet. So what I'm going to want to do is convert this data from JSON into Parquet. So I'll come in here, and I'm going to say, drop table if exists. Well, I don't have the table yet, but this is just to make it so that if I run my notebook a second time, it would drop that table and rerun this code. So the first time, this is actually kind of a no-op because the table doesn't exist. But then I'm going to say create table health tracker silver using Parquet, and I give it a location to put that file. Using Parquet, I'm going to have it break up the data on disk by device ID. I don't have to, but you're able to partition the data by different parts if you needed to on disk to make the file smaller. And then I give it the query that I want to run to populate this Parquet file, and we're going to read the original JSON data to do that. And we're going to read that timestamp that was coming in as a double, and we're going to convert this to be a Unix timestamp. And we're also going to grab the date. So we're going to grab the Unix timestamp and the date. So we're doing some data cleansing as we go and putting it into a better file format suitable for reads. And Parquet and Delta are by far the better file formats. Now, a lot of data lakes already have Parquet, which is why we started by making this be a Parquet. It's just to show you how you would do it if it was a Parquet. But we're really interested in using Delta. Delta is an improvement on the Parquet file format. So let's convert this to be a Delta table instead. So let's say that I already have a data lake that's using Parquet. Could I convert this to be a Delta table instead? And there are a variety of different ways to do this here. I'm going to go ahead and jump ahead. So first, let's look at it, and we're going to see that it is, in fact, a Parquet file. Describe detail, health tracker silver. And let's see what we find in here. It is located here. And it's partitioned by this, but it doesn't tell me the file format. So I'm going to go describe extended instead of describe detail. And this lets me scroll down and see, yes, in fact, it is a Parquet file. And I want to convert this. Oh, somebody says I missed it. Apparently, the describe detail did tell me the file format. Let's go back. Oh, there it is. First column. It was there. I was just blind because I saw the name over here instead. Perfect. So I can do describe detail or describe extended. All right, so we know it's a Parquet file. How can I convert a Parquet file? Well, there's a couple of options. I could A, leave the file alone and simply create a new one called Parquet, create table Parquet silver Delta. I could make a new file and leave the original one alone if I wanted to. And I would just change it to say using Delta. And then do a query, just like we did before, select star from the old one. I could query and make it, And this works if I'm willing to make a copy. So this would make a copy. The other option I have, though, is I could actually convert the Delta table to a Parquet, or excuse me, the Parquet table to a Delta in place without actually making a copy at all. So let's do that instead. So I'm going to come down here and I'll say convert to Delta. Let's take a look at what that looks like. Convert to Delta. And I give it the path to the file. And this is going to go to that directory on disk. And this is inside of DBFS. If I don't put the prefix DBFS, it assumes it's DBFS. I'm getting an alert that you can't hear me. Is anybody else having trouble hearing me? Just send me a chat message and let me know you're able to hear me. Sometimes there's internet issues. No issues. Perfect. Thank you, everybody. All right, so I could convert this to Delta on disk. Rather than copying the data, I'm just going to convert a Parquet directory to Delta in situ, in place. So it's going to that directory and rewriting it to be a Delta directory instead. And once I've done that, what I'm going to need to do is to re-register our table to be a Delta table. So I'm going to come in here now, drop the old table, remake the table, and I'm pointing it to where those files are. Because even if I drop the table here, because I've told it where the files are, it's actually not deleting the files on disk, it's just removing the table registration in that metastore we talked about the other day. It's just removing the identifier for the table. It's not actually deleting the files on disk in this case. It's what you call an external or unmanaged table. And so I'm just going to remove it and then recreate the table, telling it that this table, instead of being a Parquet, I've officially turned it into a Delta table. So I say using Delta. There we go. And now let's take a look at this directory. I wish I'd actually shown you what the directory looked like before and after, but let me go ahead and just do this right now. Let's take a look at this directory. So %file system, that says I'm doing a file system command, and then I'm going to list this directory. And notice that it's still the same content that I would have had if it was, notice it's partitioned by device, just like a regular Parquet directory would be. But when I converted it to Delta, it added this subdirectory here called Delta log. And the Delta log serves as this transaction log that lists which files contain the latest data. So it's really a JSON file in the Delta log, and it lists which files contain the latest version of the data. And I'm just going to showcase what that looks like here, %fs head, and I'll point out that transaction log. Notice it's just a big JSON file, and it's going to list for each partition what's the minimum and maximum value of the heart rate. You can see other information in here, like what's the schema. But the most important part of this is going to be where it lists the individual files, like this one, that represent the data. Having a transaction log is incredibly powerful, because if I go to do an update, what it's going to do is write out new files and then change the transaction log. It'll make a new entry in the transaction log saying, you know, maybe your old data set was these 4 files, but you've just done a modification to this one. So I'm going to rewrite this file out as a new file, and I'm not going to delete the old file, but I'm going to mark it old. So now my data will be this file, and this file on disk. So I'm able to access old versions of the data, that's known as time travel, and I'm also able to start writing new files, and only when the new file was written successfully does the old file get marked old in the transaction log. And so I'm able to achieve versioning as well as atomic updates. So if in the middle of a write, this failed, I would just never mark this file as good, and I would never mark this file as old. So I get transactionality because I've got this transaction log in Delta. It's a critical feature that Delta adds on top of Parquet. But if you look at the actual files themselves, so let's go in here again and look at the files themselves. The file format under the hood is still Parquet. What Delta is adding is that transaction log. And that is a critical piece to a cloud data infrastructure. Now, somebody was asking, where do the DBS files get stored? So where is this DBFS? So to answer that, I could do, for example, %f mounts, and I can see different mount points, paths in DBFS, and what bucket are they pointing to. So it could be pointing here to a S3 bucket or to an Azure Blob Store bucket. So Windows Azure Blob Store, or Windows Azure Data Lake Store, or S3. I'm able to point to a variety of different types of buckets. In this case, I'm not actually in the mount directory. So there's what's known as the root bucket that would correspond to the top. And again, because this particular workspace is deployed in AWS, that itself would map to an S3 bucket. So the root bucket, let me see if it even shows up. Here it is. Databricks root is itself a bucket in S3. Now, Corinne asked, what would happen if the table wasn't converted to Delta? Well, if the table had not been converted to Delta, it's no big deal. For example, I can continue to query the original health tracker table, select star from health tracker 2020-01. What was it called? File name. So I can query the original JSON file. And in fact, I could have queried the original Parquet file. So I'm able to use file formats that aren't Delta if I wanted to. Delta simply adds that versioning and transactionality and a bunch of indexing capabilities that make things faster. So we like Delta because it's more robust and faster, but Spark is able to work with Parquet. It's able to work with other things. I absolutely can be using other types of technologies out there. Now, some people are asking, is there like intelligent to this notepad? Does this work, for example, like Toad does for Oracle? It doesn't have as many features as some of those other SQL workpads do. For example, I have to run all of a cell or none of it, but the secret there is that if I want to run part of a cell, I comment out the part of the cell that I don't want to run. And there's little shortcuts for that, like Control/. And if you want to see the keyboard shortcuts, you would just click on this keyboard icon up here. And yeah, so Karam is mentioning if I'm doing change data capture, Delta has a lot of benefits because I can look at what's changed between each version of the table. So there's actually a lot of ways to do that. Somebody else asked, could I convert this directly to Delta and not go through the Parquet step? Absolutely. Let's do that, in fact. I'm going to drop the table, Health Tracker Silver, just to emphasize I don't have to go through this Parquet step. And I'm going to delete it on disk as well, just for demo purposes. I'll delete the files on disk. So that table doesn't exist. And he said, do I have to go to Parquet first to get to Delta? And the answer is absolutely not. In fact, normally you wouldn't go through Parquet. So instead of saying create table silver using Parquet, I could just say create table silver using Delta. And it's going to make this immediately be a Delta table. And I'm not even going through Parquet first. The only reason in this demo I made it Parquet first is so that I could demo the command convert to Delta. That's the only reason I'd actually made it a Parquet file first, is so I could showcase this convert command. But you would probably go straight from JSON to Delta, as I did here. All right, so at this point, we have a delta table, whether we went through Parquet first or not. Robbie asked, what happens if the JSON doesn't have a standardized schema? Some of them have more columns, some of them have other columns. Yes, you can still convert it to delta. It'll infer a unified schema. But Robbie, in a case like that, sometimes it helps to actually provide the schema in your create table statement. So one thing I did here is I told it to infer the schema in the JSON that we did up above. Here we go. I told it infer schema. If you don't want to infer the schema because maybe the schema is too erratic and changing, you could provide the schema manually instead of inferring it. And that would help you with data, JSON data that's sparse, where the schema varies by row. You would manually provide the schema, and that would address that concern. And I'll leave that to you to look at our ETL course. We talk about how to provide the schema. If you go onto our Databricks Academy and look at ETL part 1 and 2, you'll see how to provide schemas manually. All right, Daryl, I'll get you to submit your question to the Q&A since it's a little off topic here as opposed to the direct chat. So Rajesh asked, could we have created Delta without even mounting the JSON file? Yes, we could. So let's say I didn't even want to mount the JSON file. So let's say I don't even have a pointer to a JSON table. I could go JSON dot and give it the path to the health tracker data. So, my JSON. I could give it a path that way to a JSON file and never even make a bronze table go straight to the silver table. You could definitely do that. There are some benefits, though, to having the bronze data available under a table name. Because then if people need to get to the bronze data, they still can. All right, so at this point, what we've just done is we've created a table designed for query purposes. And at this point, it is a delta table. And I'm able to, in turn, query that table. And one thing that you'll note is that it queries a lot faster than it used to query if it was a JSON file. So now notice I'm getting sub-second query times because Delta and Parquet are much faster than parsing JSON. And now, in the interest of time, I do want to keep moving forward because we have a lot more work to do. Just because we've got a silver table doesn't mean we're done. So let's go ahead and continue on. First of all, let's use the describe command, describe detail or describe extended on our silver so that we can see that, in fact, it is a delta table. So describe detail. Notice this time it says the file format is delta. And again, it tells me where it's located on disk. Now, let's keep going. So let's do a more interesting query. I'm going to just steal it. It's not that much more interesting, but instead of just describing it, let's do an aggregation. Count star from health tracker silver. Here we go. Count star from health tracker silver. Now somebody had asked, could I do this in Scala? I'm going to just showcase that yes, if you wanted to use Python or Scala, you could. I'll do Scala. I'm going to run Scala code. Notice the default language for this notebook is SQL. So if I want to run Scala code, I have to say it's Scala, but then I could go spark.read.table, health tracker silver .count, and I could display that. And I could write the exact same code in Scala. And why is it complaining? Oh. Well, count in this case is coming back as a single row. So we'll do this. And I get my count back, 3,720. I could do this in Python. In this case, the Python would look exactly like the Scala. There it is in Python. If it was Scala, technically I don't need these parentheses. There you go. So just showcasing that, yes, I could mix in Scala if I wanted to. We're going to stick with SQL for the bulk of this particular one, but if you wanted to learn how to do this stuff using Python and Scala, I really do recommend you go to databricksacademy.com and get the ETL course series. ETL is part 1, 2, and 3, and they use Python and Scala to do this type of work, and you get to choose your programming language. For this series, we're going to focus on SQL for today. We'll have a little bit of Python tomorrow on session 3 and quite a bit in session 4. All right, let's continue on now. So at this point, we have loaded our silver table, which serves as that single source of truth. And now we want to try to create an analytics table that does some degree of aggregations. So let's go in here and create a Delta table. Now, if you're running the course yourself, you'll notice that they recommend you delete old files if they exist on disk. This is just to ensure that if you run the notebook twice, there's not old files laying around. I don't have that problem because I don't have old files laying around. So I'm going to go straight to this command here, where we're going to create a table that does aggregations. So this is my gold table. It's the data mart table. So I'll drop it if it already exists. In this case, it does not exist. And I'll create the table using Delta. I can tell it where I want to put the table on DBFS. And then I give it the query to use to make that table. So in this case, I'm going to get the average, the standard deviation, and the max of my heart rate. And I'm going to group by device ID. So I'm making this gold table. And let's take a look at it. Select star from Health Tracker User Analytics. And there it is. And notice that, of course, the device IDs didn't come out sorted in any particular way. So when I go and make a bar chart for this, let's see here. If I make a bar chart, I want to use device ID, and I want to look at max heart rate, average heart rate, and standard deviation here. And I click apply. Grr, notice that these keys came out in a weird order, 0, 4, 3, 2, 1. I don't like that. So I could come in here and go order by P device ID and sort as part of my query, and now they come out ordered. Very cool. And this is my gold table that my end users might want to hit as part of their exploring the data. So first I read in those bronze JSON files. I then did cleanup. I fixed the schema and I brought in the data. And that's my silver table, although we still have some cleanup to do. We're going to be doing that soon enough. And then I was able to build my gold layer, which is these reports and roll up analytics. And somebody asked, why is the gold table not created directly from the silver? And it is. Take a look. I made the gold by running a query off the silver table. Now, if I wanted, I could actually run that as just a SQL query and not write it out as a table. But that means that every time I run this query, I've got to do that computation over again, which for really big data could take hours. So by saving the results off as another table, I'm now able to hit that table and view pre-computed information for my exploratory data analytics. So the benefit of writing a gold table is speed. It takes a little while to write out the results, but now let's say that gold table had millions of records in it. I could query the gold table directly and not have to recompute all those aggregations every time. So yes, they could query the silver table directly, but at that point, they've got to run those analytics over and over again. So if these are analytics that they're reporting on frequently, for example, if I'm building a star schema and I'm creating a cube, a data cube for a star schema, I likely will want to write that out as a table so that people can query it much more quickly than they could query by recomputing the aggregations on the raw data every time. But you have a choice. It depends on your use case as to whether or not you want to query the silver table directly, or you want to write that out to a gold table so people can look at the roll-ups more quickly based on pre-computed aggregations. And that's a choice that depends on your use case as to whether you need this gold table layer. But the more data you have, the more benefit you get from having some pre-computed gold data. All right, let's continue on here. Let me look, first of all, take a brief moment and see what kinds of questions I'm getting. Some people have asked, is the notebook approach the approach that people like to do for ETL jobs on Databricks? For ETL jobs, we really do like using notebooks. You actually have choices. You can upload, for example, a Java archive or a Python file. You can use notebooks. You can also use ETL tools integrated with Databricks. And then if you're in Azure, there's something called the Azure Data Factory that you can also use. But notebooks are a really nice interactive way. You can also use Airflow. That's right. Somebody just mentioned you could use Apache Airflow to kick off those ETL jobs. But what we like to do a lot of the time is to describe the ETL in a notebook and then have Airflow call the notebook, or Azure Data Factory call the notebook. Or if you have a file, like a library you want to use, you could upload the library to the cluster and then have the notebook call that library. So there's lots of options that come with that. Saeed, I see earlier you would ask, you need to find a schema for JSON. Yes, you can. I'll let you look at that ETL course for examples of defining schema for JSON. Or if we have time, I will try to pull up an example where I defined a schema for a JSON file at the end of the course. Let's see here. Just going to skim down to some of the newer questions. Somebody asked, could we use this with structured streaming? Absolutely. All of the things that we're doing can be used with structured streaming, and that will be something we showcase in Seminar 3. And then Nimesh mentioned, could we create a multidimensional cube on top of a data lake? Absolutely. So there is, in fact, a cube function that I could run. I may have to look up the syntax for cube because I'm not using it right. It is average heart rate. Oh, I know why. That was my gold table. Go back to my silver table. I could, for example, do a cube. And I just have to remember the syntax for doing a cube, so I may be in trouble here. I don't remember the syntax off the top of my head, but I can use cube functions inside of my SQL to roll up a cube. And if you really want to know what functions there are, I have a bookmark to it. But if we go and look at the functions that are out there, there is a cube function for building cubes and rollups. Oh, it's called, let's see, rollup. Why is it not showing up? Oh, I'm looking in the wrong place. That's why it's on the data frame itself. So we have to go to the data frame API and we look at cube. Shoot. This is what I get for answering questions live. But let's see here. Spark, data set, cube. There it is. There are functions that we can use, and you could do it in SQL as well. Databricks, Spark, SQL, cube. And in here, let's see if we can find where cube is mentioned. I will have to look and answer that offline, where we find the cube operators inside of Spark. I believe we have an online presentation, in fact, where people are using the cube operations inside of aggregate in Spark. Let's go ahead and not get sidetracked by using cube for right now, because we do have a lot to cover today. But the answer to your question is yes, I could do cubes in my rollups. All right, let's continue on. And we've created our dashboard. I already showed you the dashboard where we got to look at our various user analytics. So let's continue on now and start dealing with newly arrived data. So I've already got my bronze JSON file, my silver query table, and my gold aggregation. And now I want to deal with appending new data to an existing file, because it's rare that you would just be done once you've built your silver and gold tables. So I need to be able to insert new data into this. In this case, I want to insert data for February. So I'm going to need to say insert into my silver table. So let's come down here and actually do that. I'm going to insert into Health Tracker Silver. I'm going to need to, again, take that bronze data that we had before, make sure that I'm making it match the schema and doing the cleanup. So I'm going to grab the bronze data for February and insert it into my silver table by using the insert into Delta command. Now, if I was doing this as Scala, for example, do this. I write my query. Then what I could do is go write.mode append and tell it that I want to write to my silver table. So, but if I'm using SQL, I just get to use the insert into command to be adding data to my file, which is really, really nice. So I've added it in here. I now have more data in this file. Let's take a quick look at my thing here. So let's go describe history, health tracker silver. And you can see that I have a new version of the table that's been written out as a result of a write operation. And it's written out new files to disk. So, and let's see here, the total number of rows, let's see, which one was version 0, which one is version 1? Version 1, okay, that's the newer data. And I could see, for example, how many files were added, how many bytes are there, and so forth. And I could even go and look at the directory. Let's go to the directory for my silver table. And let's look inside of one of these partition folders. And you see that it's written out another file part. It's appended a second file to the first. And now we haven't deleted anything, so both of these files are considered good. None of them have been marked invalid yet. But if they were marked old, that would have been marked in that metadata directory that we talked about, the JSON log or the Delta log. So if I look at the Delta log, you see that I've written out a new record to the Delta log that says, what's the new state of the files on disk? And this is constantly being appended to let me see the state of files on disk as I add new files or delete files from the table. All right, let's continue on here. That was an insert into. What if I wanted to view the old version of the table? So right now, when I want to run a query, let's just run a query on it and not do time travel. I want to view the current state of the table. There we go. The current state is 7,105. If I wanted to view, though, the earlier version of the table, I can say version as of 0. And I get to view the original version of the file, the 2720 versus 7105. So I've added quite a bit of new data to my file. Now, let me go back again and do describe history Health Tracker Silver. And let's grab this timestamp. I could also do timestamp as of and give it a specific time. So let's go to a time that was a little bit earlier. There we go. And this time is between the two, so it'll automatically figure out that it should show me version 0. So I'm able to view previous versions of this data. I could even do a query where I get to see what's changed. So I could say select star from Health Tracker Silver minus select star from Health Tracker Silver version as of 0, and see what's changed between the two. What did I do wrong with my version as of? Fix that. Version as of 0 should be working. There we go. And I could see what changed between the two versions, which is really cool. Somebody had noticed in the courseware, the course has this tip. They say you could go spark.sql.conf and change the number of shuffle partitions. So you go %SQL set conf or set spark.sql.shuffle.partitions and change the number of shuffle partitions. That's a performance tuning option. If you have a small cluster, you'd set this to 8. I actually have a much bigger cluster with 64 cores. Depending on the size of your cluster and the size of your data, this is a setting that you can change. I deliberately did not go into this, but somebody noticed that it was in the written courseware. And I didn't go into this because I didn't really want to explain what this setting is all about right now. It's a performance setting thing. The course suggests that you set it lower for your smaller clusters to make things run a bit faster. We're going to just sideline that discussion because it's really a performance tuning topic. The default is 200, and it works very well for both small and large data sets. So we normally don't recommend changing the default unless your data is truly small enough that you can afford to go smaller. And in our case, our data is in fact small enough. But I'm not going to go in any more detail than that. It's just somebody had asked a question several times asking what happened to that, and I just had skipped it intentionally. Let's continue on. So at this point, we are able to do time travel to view earlier status of the table, which is really nice. And if we don't tell it a version, then we're seeing the most recent version of our table. So at this point, in the previous lesson, we had done a batch update to the silver table, and we were able to count things. But there are actually some missing records in our data. And to discover that we've got missing records, let's run this query. Because during ETL, sometimes you didn't ETL correctly. So here's an example. Let's just run a query on our silver table. And notice that one of the devices has significantly fewer records than the other devices do. Here, I'll even order by P device ID. So it's in order. And you can see that row 4 has fewer records than the other device. I could even do this as a bar chart. And I see that I've got fewer records. And this is not unusual that you do an ETL and you discover, oh, the data that I used when doing the ETL is out of date. So, or it was wrong. And now I've got to go back and do some corrections. So that's what we're going to deal with next. So we could try to do a plot here to get a sense of the missing records. So in this case, I could do select star from health tracking silver, and I could just look at devices 2 and 3. And in this case, it's not going to show up in a really pretty plot because I'm not grouping by date. Well, let's see. Let me come back. If I go select, let's run this query. I may have to tweak it a little bit, because when I run this query initially, it's going to be a little bit cluttered. Oh, there we go. It's actually not too cluttered. You can see that I am missing some data for certain dates. And let's try to make it match a little bit. So I want to look at the date and the count of the records. So I'm going to come in here, plot options. I'm going to look at the date, and I'm going to look at the count, and I'm going to group by device ID, and I'm going to look at just the count of the heart rate records. And what I see here is that I've got most of the data, but I'm missing device 4 starting at a certain date because the input data that I ETL'd was missing it. I didn't have it. So we're going to need to go and backload some data and update our table to have this new missing data. And that's an incredibly common type problem. So let's address it. We have clearly some broken readings. So we're going to first create a temporary view to identify our broken readings. So let's talk about what a temporary view is. So I'm going to create a view. A view is nothing more than a stored query. So unlike creating a table, which should be written to disk, a view is just a query that whenever I query the view, I'm really running this underneath query. And I'm going to count how many of these exist where the heart rate is less than 0, because those are some broken records here where I had these negative heart rates. And let's query this table now. So I created a view that I could turn around and query. And the view is not written to disk. It is really running this query underneath every time. And sure enough, I have quite a few readings where I've got negative heart rates. And this is leading to some data corruption. So there's a lot of problems in my data. I've got missing data, and I've also got negative heart rates that's dirtying my ETL. And I need to go back and fix this. So let's first display them. So we could run just a little plot here. That's what we did down here, but let's turn this into a plot because I think plots say a lot more. So let's do it by date. So I'm going to come in here, do a bar chart by date. So I go plot options. I want to look at the count of the broken readings grouped by date. And let's see here. Oh, I've already got the count. My bad. I don't want the count. I want the actual values. There we are. And because I already had grouped them by count up here, I didn't want to count the count. That wouldn't have worked. And you can see, yes, indeed, I have broken records for some of our data that I need to go back and correct. And this is a typical thing to happen in people that are maintaining a data lake, is that dirty data gets in there, you discover it later, and you've got to go and do corrections or updates to your existing table. So how do we go about doing that? We could also get a count of how many total broken records there are. I could sum them up. There's 67. I'm going to skip doing that, summing up the counts for a total of 67 broken records. Let's repair them. And the way we do a repair in Databricks is we're going to use what's called an upsert. And an upsert allows us to merge in corrections to our existing table. So to do that, the first thing I need to do is to grab the data that I want to do corrections on. So let's grab the data that we want to do corrections on. So we're going to make a temporary view, updates. And this is just a query here. I'm going to look at the each partition. So this is actually using what's called a window function. And we're querying the silver table, and we're looking at what is the first and last heart rate in a window of time. So we're looking over, in this case, over the device and the date. And we're trying to get the first and last heart rate, and we're going to average the two, the minimum and the maximum. We're going to average the two to make it a heart rate, because what we had was some duplicate data and some negative data. So we're just going to write a really fancy query that's going to average the two, but only in cases where the heart rate was less than 0. We're going to instead average them and get something better than the 0. Just a way of doing analysis to correct for bad data. And let's just take a quick query of our updates table. Or updates view, I should say. Notice defining the view took no time at all because it didn't actually run anything. It just defined this as a query. It's actually doing the math when I query the view. It's lazy. But now notice that my heart rates are positive, although I have a few nulls in here. Otherwise, my heart rates are positive. So this is a way of correcting for bad data. So I just want to go back and talk. So there was a bunch of missing records, 95 missing records, and 67 records with broken negative readings. So there's things that we could do. We saw that we could append files, but in this case, I want to go back and modify existing records. And this is where we're going to use merge to modify existing records using a process known as an upsert, which means I'm going to update the data if it's there, insert the data if it's not there. And to do that, we ran this query to simply compute a replacement by averaging the good data. We're going to replace bad data with the average of the good data. Just taking a quick peek at questions. Looks like we're good for the moment. All right, so we want to do updates here, and let's just compare the schema for Health Tracker Silver and Health Tracker updates. Let's make sure that the schemas match. So we have name, heart rate, time, date, and device ID. We could actually do describe to look at the two schemas, and we want to make sure that they match in order to be able to do this update. Updates. And let's see, we have name, heart rate, time and date, and device. Name, heart rate, time, date, and device. So our schemas match. That is a very good thing. So we'll be able to do a merge operation. The other thing we might want to do is make sure that the new readings, so if I do a count star from updates, notice that I'm putting in 67 new records, which matched the number of broken readings we had before. And this is the type of thing that a data engineer or a data scientist needs to do. We spend a lot of our time cleaning broken data. So a robust data platform needs to be able to clean broken data. And the Upsert operation we're about to do doesn't work on Parquet, but it will work on Delta tables. So let's get to where we do this Upsert. So first and foremost, let's make a table that's going to describe all of the tables that we want to insert. That's the new data. And all of the tables that we want to update, that's the updates table. So we're going to make one table that's got the new records I want to insert. This is coming from this new file that represents our missing data. Whereas update is the data that was broken because we had negative values. So we have a table for inserts, that's the data we want to insert, and a table for updates, that's the data we want to change. Let's make a view for each of these so that we can then get to the command I'm really interested in, which is this merge command. I'm going to insert this data. I'm going to be updating this data. How do we do that? This is the secret sauce, the command I've really wanted to get to. Merge. So I want to merge into my silver table. I'm going to grab things. Where's the Upsert table? Hang on here. Did I miss a step? I may have missed a step. Let me look. Ah, yes, I did miss a step. So I told you we had the things we wanted to update. We had the things we wanted to insert. For the sake of it, let's pretend like we've just got a data of corrections. We could call this corrections. In this case, we're going to call it upserts. But it's a table that's going to represent all the rows we want to change, as well as all the rows we want to insert. We're just putting them together into one new data set that we want to upload. So now I want to merge this new data into my table. So let's just do a quick query. Select count, or just select star from upserts. And this is all the data that I want to add. Some of the data is going to be an insert. Other data is going to be an update. So I want to go to the silver table. And if there is a record that matches the device and the time, if it's already in the silver table, so when it's matched because it's already in the silver table, then I want to do an update command. Update and change the heart rate for that timestamp so that it's no longer negative. But if it's not in the silver table, that is when it does not match, then instead of doing an update statement, I want to do an insert statement. And I'm going to insert this new data into my table. Merge is how we do this update or insert in Spark, in a data lake or a delta lake. And merge only works on delta tables. So I can't use the merge command on JSON. I can't use the merge command on Parquet. I need to be working on a delta table to use the merge command, but it's going to let me merge in fixes to my data. If the data matches record that's already there, I'm going to change the record that's already there. If it's not already there, then I'm going to add it to my table. So let's run this. And then let's do describe history and look at my silver table. This upsert, this merge operation, is how you are going to repair broken data in a table. So here we go. Let's describe the history now. And we could see I have version 2 now available that was the result of a merge operation. And looks like we've got a bunch of files that actually got added as part of this process. A bunch of small files got added as part of this process. And you could see some of the files were deactivated. Here we go. Here's how many rows I inserted, 95 rows. It looks like I updated 68 rows for a total number of rows in my table that are 7,000 rows split up into 1,000 different files. Now somebody asked, is a view of a delta table also a delta table? The answer to that is a view is not a table at all. It is a query result, and it's not stored anywhere. It just gets computed when you query the view. So views aren't really physical files at all, so that you wouldn't call them delta, you wouldn't call them JSON, you would just call them query results. So a view is a read-only query result. All right, so we have written this out, but I'm a little bit concerned about how many files I have. I have 1,000 files that got written out. That's a lot of small files. So I'm going to jump ahead. We do this technically later in the course, but I'm going to jump ahead a little bit and showcase the optimize command. I can give it a table, and if I tell it to optimize the table, it's going to compact all of the small files into a big file. Now, Yash just asked, didn't we already append data? So previously we had appended data, but then we discovered that there was dirty data, and we wanted to append some new data, and we also wanted to fix some negative values. And that's where we did the upsert. So in this narrative here, we weren't just appending anymore, we're actually fixing. And it's contrived because I wanted to show you the merge command. So the insert into only appends, whereas the merge command appends and updates both, which is really nice. But now here I did this optimize command, and it removed 1,000 files and leaves me with only 5 files that are larger, so that querying this table will now be much more efficient. So the optimize command will compact small files into big files, speeding up queries. I wish I had done a query before I optimized. Actually, there's a way to do that. Let's do select max star or count star from health tracker 0, version as of 1, and compare it as of our latest version 2. I just want to show you the performance difference I get by optimizing the table, because I don't want to read 1,000 files if I could get away with reading only 1 file. Oh, shoot. In this case, the query optimizer is cheating me, because what the query optimizer is able to do is get the counts from the metadata, and it's not even looking at the data on disk. So let's do this instead. Let's just do a select star on both of these. Oh, I know what I could do to make it touch all the data. I could throw in a distinct. I want to keep the query optimizer from being able to be too smart, because I want to show the performance difference. So if I do a distinct, it's going to actually have to read all the data. So version 1, doing a distinct operation, took 3.68 seconds. Version 2, with fewer files, let's see how long it takes. Oh, it took longer. Well, that made a liar out of me. Maybe it's versions 3 and 4. I bet you that's it. Let's go back here. It's versions 3 and 4 I want to be comparing, or 2 and 3. Okay, it was versions 2 and 3. Version 2 was the merge. Version 3 was the optimize. Here we go. So I want to compare how long it takes to compare version 2. It takes roughly 6 seconds to do version 2. Let's find out. 7.5 seconds, whereas our latest version that's optimized took 0.95 seconds. Because what it did is it compressed all these small files into fewer big files. So often when we're doing manipulations on our data sets, we end up with this file fragmentation problem. And the optimize command is part of Delta, and it speeds up the performance by reducing the total number of the flans. Now, somebody asked, why isn't optimize just done automatically? There is, in fact, a way we can turn on auto optimize in Spark. In this example, optimize was not enabled to be automatic, but there are some settings that we can configure there in the Databricks documentation to turn on auto optimize. The reason we don't do it automatically by default is that the optimization command itself, you notice, took 25 seconds to run. It took 25 seconds to run. So you have to decide how frequently you want to optimize. And there are ways you can configure Databricks to do it for you whenever it thinks it's time to optimize. But the optimization step will take time. But once it's optimized, your queries will be a lot faster, which is really, really nice. And now Jesse asked a good question. He said, did it leave the old files in place? And the answer is yes. That's why I was able to query the old version and query the new version. The old files are still there and I can time travel to them. But if I query the latest version of the data, I'm getting those new optimized files. The reason we do that is because you don't want to just delete the old files on disk while other people may have a job running that needs them. So by default, Databricks is not going to allow you to delete those unoptimized files for at least a week. We want to leave them around for a week to make sure that any queries that are still running still have access to the old files. And then there's a command we can run later called vacuum that will delete the files after a certain amount of time has passed. And that's actually going to come up in our course. So I jumped ahead a little bit because I just didn't like seeing 1,000 files. We actually teach optimize and vacuum further downstream, and I just moved it up ahead a little bit. Now, we are going to run out of time very soon, and I wanted to be a little bit further ahead than we are now. Let's see. So we just did the Upsert. We saw now that we can do counts and we could do time travel. So let's see here. Let's do the count of the number of rows before we did the Upsert and compare that to the number of rows in the latest version of the data, just to see that we did in fact repair our table. There we go. I have new rows added, 85 new rows, and 65 broken rows were also fixed, which is really cool. That's the merge command. It's what allows us to do these updates in an efficient format. The reason we want to use the merge command is because we don't want to run a single update line by line by line. That would be very row. We want to do batch updates. And that's where the merge command kicks in and is incredibly powerful. All right, let's see if we were at a good stopping point. Yep, I showed you describing the history of the table already. So you were able to see the history and the merge and the optimization. We can do an additional Upsert next to deal with broken readings. I'm going to save that for, I believe, the next course. Let's see here. We still have to deal with, where are we? Oh, good. We are pretty much on schedule. We will do the second insert as a review in the next session. And then we will deal with deleting old records. We'll talk about optimizing, and we'll talk about GDPR compliance and streaming in the next session. So I'm going to leave this last Upsert for next session because it'll serve as a good review of doing Upserts. In the meantime, you guys, again, remember the link. It was tinyurl.com/, let's see, I'm going to scroll up on our chat history and grab it. tinyurl.com/cloud-data-platform. Let me go back in our slides again. tinyurl.com/cloud-data-platform. And at this point, I would like to take some Q&A and questions. And remember, there's lots more training available on the Databricks website. Here's a short link to the Databricks website, or academy.databricks.com. We have live online training that you can take. You can even register for a 3 or 4 day class. We have performance tuning classes that go deep into how Spark works. I really love our performance tuning courses. There's also some really good self-paced training for people just getting started. And if your company becomes a Databricks customer, we make that training available for free. Otherwise, you can simply purchase the courses on our website. If you'd like to talk to somebody at Databricks, feel free to go to this link, bit.ly/contact-us-Databricks, or DB. And you could speak to one of our people about using Databricks or setting up a trial of Databricks for your company. Now I'm going to go ahead and answer some Q&A that people have. Let's see here. There's one question about Azure Data Factory. That's a little bit out of scope. So Daryl, what I'm going to suggest is that either have you reach out to support or follow up offline for that question. But really, if you are able to reach out to our support team, we should be able to help you a little bit with using Delta as a sink for Azure Data Factory. We have built in some integrations. Somebody else had asked, could I use Delta with Data Factory? Yes. Can I use Delta with Athena? The answer is yes. There is documentation for how to do these things on the Databricks website. So if I search for Athena or Presto, for example, Databricks, Delta, Athena, there we go. There is a link, Presto and Athena, Delta Lake integration, and it talks about how to do it. Let's do the same thing here. Instead of Athena, let's use Azure Data Factory with Delta. Where is it with Delta? Delta loading from database using watermark with Azure Data Factory. And we search for the word Delta, and there's a nice example article there for you. Let's take a look at some other questions in here. People want to know, where can you get this notebook for practice? And rather than distributing the notebook that I just wrote, what I'm going to point you to is that link again that we gave you here, cloud-data-platform, and that's going to let you access the source materials that I was using. So you'll be able to go through this on your own and actually run it. I do think there's a lot of value in having the instructor, me here, explaining what's going on and giving you that extra level of depth beyond this, as well as answering questions. But I really recommend people go and actually try this out yourselves. You're able to do it if you just come into the Databricks Academy link that I just gave you and do the Delta Lake Rapid Start with Spark SQL. And for those of you who are interested in it with Python or Scala, they are working on a Delta Lake Rapid Start in those other programming language. It's just not been released yet, but I think there's a lot of value in learning how to do it with Spark SQL as well. And if you're watching this in a recording, check the website. Those may at some point be released relatively soon. I know we plan to do that this quarter. Does Optimize have an impact on version history? Was a question Farouk asked. And the answer to that, we actually saw. If I show the history, so if I do describe history, I am able to see a new version of the history show up in this history. But it's actually marked as, let's see if I can find it. Well, you don't see it in here, but in the metadata, it knows that the optimize command doesn't actually change data, it just reorganizes it. So if I was to ask what's the difference between version 3 and version 2, Spark would immediately be able to figure out that there was no actual data changed. It was just a reorganization of files. So if I was doing an incremental change data capture, I could very efficiently determine that the optimize command didn't change anything. And that's some of the metadata that's stored in that JSON file in the JSON log. Let's see here. Other questions that people ask. Are there any recommendations of optimization that Databricks is providing when we execute SQL rather than blindly providing the optimize command? So the optimize command is actually really smart. Its job is to combine small files into big files. If I was to run optimize twice, you'll notice the second time I run optimize is actually going to be very fast because it's already got big files. So let me see if I can find where the optimize command was. There it is. So the first time I ran it, it took 25 seconds to combine small files into big files. The second time I run it, boom, 1 second, because it's determined it's already optimized. I don't need to do it again. So typically, you're going to do optimize after a big ETL operation. You're going to do your ETL, and then you're going to run optimize, so that people who are querying the tables are querying optimized versions of those tables. So optimize when you're complete with your ETL. I wouldn't optimize every step in the middle of my ETL because you're wasting time. The real goal of optimize is when you're done with your updates, make it fast. And that would be the guidance that I would give you. Somebody else asked, is time travel only possible past 1 week? So time travel is possible as long as the old files are still around. So I will be able to time travel indefinitely backwards in time until somebody vacuums up the old files. So when I run a vacuum statement and I'm deleting old files, that's when I can no longer access old versions. Now, vacuum by default is going to retain things that are newer than a week. So it only is going to get rid of versions older than 1 week by default. And my data has nothing that's older by 1 week. So you'll notice that I'm still able to time travel all the way back to version 0. Now, if I never ran the vacuum command, or if I set the retention period to be a year, and you can tweak the retention period of the vacuum command, if I said, no, I want to be able to keep stuff for a year, then it won't delete those files and I'm able to time travel further back. But time travel, once you vacuum and the old files are deleted, you're no longer able to go that far back. So if I was to lower the retention period from a week down to a couple of hours, I would in fact get rid of old versions. And that's something that we're going to do as part of GDPR compliance. So in the next session, I'm actually going to use the vacuum command to intentionally clean out old copies of the data so that I can tell the customer that I truly have expunged their information from our system as part of the European privacy regulations. Now, Amalan asked, isn't the number of files based on the number of partitions? And the answer is yes. You'll remember initially, after I did that merge, I had 1,000 files and 5 partitions. That meant I really had 200 files in each partition. Where did that 200 number come from? And the answer, it was that spark.sql.shuffle.partitions, or num partitions, I'd have to look up, as 200. So each partition had gotten 200 files because it was a sort operation involved in my merge, and it had to shuffle the data. So 5 times 200 gave me the 1,000 files. And I really only wanted 5 files because they were small, so I used optimize to compress them back down to be a smaller number again. But each partition will have a minimum of 1 file, and a maximum could be thousands of files. And so what optimize did is it grouped files within a partition. So somebody else asked, how do you do incremental loads? That will also be a topic for the next session. So I'm going to encourage people to come and attend the next session where we use streaming to do incremental loads. Others are asking where to get the recordings. That information is being made available on the webinar website. So the website that you used to sign up for the webinar, you'll be able to see information about the recordings as well as in the follow-up emails. And now we have hit the 2-hour mark. So I will stop here and thank everybody for attending and invite you to come and attend again tomorrow. Looking forward to it.